So how does a setting for microbiological sampling of foodstuff looks like? Well, I'm gonna start over here. It's kind of nice to have everything on hand, and it all starts with the safety, right? So the first thing I would normally do is to disinfect and clean the whole area where I'm gonna work. I've done this before our short video, so I'm going to go ahead and explain what everything else does. We're gonna need a Bunsen burner. That's what we still work on, although today we have other options as well that do not need a connection to gas. But for this laboratory, we use a Bunsen burner, which is connected to the gas knob. I'm gonna start by actually starting the Bunsen burner on, because I know for myself that in food microbiology, I want to be safe. So I want to be able to work in a aseptic area, and the first thing that I do is to start creating my aseptic area. So the first thing I'm gonna do is to turn on my Bunsen burner. I'm a little bit shorter, so I'm gonna have to bend a little bit. It is quite important that the gas knob is turned completely on, so not partially but completely on, and that is to make sure that the flow of gas is fluid, that we don't have any turbulent flows or any interruptions. And when it's completely turned on, then I know for sure that my gas flow is going to be constant. It's still safe to talk because I didn't yet turn on the Bunsen burner from this side, so the gas flow is not still there. I do want to make sure, however, that I've got a lightning source close by, and I wouldn't start talking without having this Bunsen burner off for the first time. So my gas is on, my lighter works, and I'm going to turn on the gas flow while approaching with the light. Slowly. Yes, and I'm also going to control the oxygen flow so I can actually see my flame. By seeing the flame, I know how high it is, I know about the debit, and I know how to be safe. You don't need to have it all the way up. You have to imagine that this Bunsen burner is going to create an aseptic zone, and we normally say that it's around 20 to 30 centimeters around the Bunsen burner. So what I'm gonna do right now, since I've seen that the flame is the correct size, I'm going to control the oxygen flow until I make my flame. We say this a blue flame in microbiology, and I do like to hear it. If I hear it, then I'm quite happy with it, and then we're ready to go. All right, so we're safe. We have created an aseptic zone for us to work in. Quite important, about 20 to 30 centimeters around the flame. I often do my fingers like this to be able to imagine how these 20 centimeters would look like in reality. This means that if I would be around 20 to 30 centimeters around the Bunsen burner, I can work aseptic. So whenever I need to open up my Petri dish, or if I want to do some pipetting over here, it should be within the Bunsen burner aseptic zone, right? All right, so let's continue. What's up next? Well, what do we need? We are in food microbiology, so we must need a food sample. It stands over here, and if you guys remember from the previous steps, this has been treated in a particular way. And perhaps it wasn't quite obvious why we do that, but it's a little bit complicated in food sampling to place the whole food directly on the Petri dish. Why is it complicated? Because the purpose why we're doing this is to be able to count colony forming units later on, or aka bacteria on Petri dishes. So to be able to do that, we need to see them, and we need to see them separately than the plots of foods that are normally in there. So liquid foods are the way to do this, and if the foods are not naturally liquid, like very rarely soups, right? Most of the foods are more complicated than just being simple liquids. We need to treat them a little bit before by placing them in the dilumat, the machine that I've told you before that is placing a known amount of peptone physiological salt, and then later on it's going to be squished and mixed together in a stomacher, right? So this is how it looks like. I've had it hidden over here all this time. This is the stomacher bag. Inside I've got my food sample that has been diluted with peptone physiological salt. It has been also quite thoroughly mixed inside the stomacher, and as I mentioned, not longer than 2 minutes, because I didn't want it to warm up and create microbiological growth that it would not be real with the real amount that it's inside my food product. All right, so we've got this one. It stays over here. I'm gonna put it aside for now because I'm gonna continue explaining what else we need. Bunsen burner, food sample that is liquid and good to be used, checked. Let me put this aside. What else? Where I said that we're gonna need to make a dilution series before we actually put it on the plate. Why do we need this dilution series? Well, we need to gradually dilute, right? In a series, it's normally a 10-fold that we use in microbiology. We need to gradually dilute this until we reach an amount of colony forming units per milliliter that we can count. If I would take it directly and there would be a lot of bacteria inside, it's going to be problematic to be able to count them, at least directly in the Petri dish. So we need to make sure that we have some amount that can be counted, and especially when we do it blindfoldly, meaning we don't know exactly how many microorganisms are inside, then we're gonna have to make a dilution series and hope for the best that when we finished, at least 2 or 3 of these Petri dishes can be counted. So what do we need? We need sterile tubes filled with peptone physiological salt. These have been pre-filled with PFZ water or peptone physiological salt in long with exactly 9 milliliters. We need exactly 9 milliliters so we can come in with our 1 milliliter, and together with a 9 is going to make 10 milliliters of fluid. So if we would start with 1 milliliter of sample that will eventually become 10, it means that we make a 10-fold dilution. And this 10-fold dilution that we're going to start over here, I'm actually gonna name it. That's what we do in microbiology. We make sure that we know what everything is. So I'm going to place the label. I'm gonna say this is number 1. It's over here. And from number 1, I'm going to take 1 milliliter and I'm going to place it in tube number 2 that also contains 9 milliliters of peptone physiological salt, sterile. I'm gonna mix it and place it in tube number 3. Tube number 3 is going to serve as input for tube number 4. Tube number 4 is going to serve as input for tube number 5. Tube number 5 is going to represent the inlet for tube number 6. And finally, tube number 6 is going to be the material that we need to grab 1 milliliter and place it in tube number 7. So 7 tubes that we have over here, normally they represent a magic number in microbiology, right? No, it's just a joke. We don't think of magic numbers. We have to think it through. Why do we need these 7 tubes? And the reason for that is that we're trying to aim for an amount of colony forming units that we can actually count on the Petri dishes. And if there are a lot of microorganisms inside a food product, normally we should be able to see, especially if there are spoilage microorganisms, we should be able to see them, we should be able to smell the product, and we should be able to see the growth inside the product. However, if we are able to do so, if I would grab, for example, just 1 milliliter and plate it immediately, I should have so much growth on the Petri dish that I could not be able to see separate colonies, hence I cannot count. So for this reason, we're doing a dilution series, and for this reason, we're trying to aim for 7 tubes, and hopefully, even in the worst case scenario where the food product contains a lot of microorganisms, we can still have 2 or 3 Petri dishes that can be counted. So that's why we go all the way to 10 to the power of 7, but there's a minor detail that might escape us, and that is that the food product had originally been diluted already 10 times with the dilumat containing 10 times more peptone physiological salt. So that's another extra that we add to the calculations later on. And even more so, by grabbing only 1 milliliter and placing it here, I'm later on going to, and we're going to see this together, I'm later on only going to place 0.1 milliliter, so it's another 10-fold that we're counting down for our calculations, but that's for later on. So alright, let's continue. We've got Bunsen burner, we've got sterile peptone physiological salt tubes pre-filled with 9 milliliters, so I can add my 1 extra and come up to 10. That's how we make a 10-fold dilutions. And how am I going to do that? Well, I'm going to need a pipette, right? I've got a pipette right over here. It's already set on 1 milliliter. If you guys don't know how to do that, you gotta check the other video that it explains exactly how to use a thin pipette, a pipette just like this one. It's preset on 1 milliliter or 1000 microliters, and beside the typical pipette, you're going to need as well these typical tips. In microbiology, we use filtered tips. I'm going to go ahead and do something that I should not do, and that is to grab one with my fingers, just to show you guys, right? So there's a special pipette tip that we use, and it contains a filter inside, and this filter is going to help my pipette stay as healthy as possible for as long as possible. This means that I'm preventing aerosols coming from the microbiological suspension that I'm grabbing with my pipette to come inside the whole pipette equipment. So when I'm putting it in, Again, this is just to show you guys, I'm not normally adding a tip like this. So when I'm adding it in and I'm actually sucking in the fluid over here, my microorganisms would eventually stay here because this is a filter that stops the aerosols from climbing into the pipette and hence spoil even later samples, right? So I'm going to discard this for now. So we need a pipette which is preset on the amount of milliliters that we need. The sooner the better. We need filter tips, especially meant for this pipette. I normally go ahead and grab everything I need before my whole experiment starts, and I also took for myself a smaller pipette, a smaller volume pipette. This is 100 microliters, which means 0.1 milliliters. So again, I'm going to repeat this: 100 microliters, so it's a 0.1 milliliter setting on this smaller pipette. Again, it comes with its own sizing match filter tips, so then it can match the size of this ring over here, and I'm going to use these ones later on when I'm grabbing microbiological material from my tubes to my Petri dish, because I've mentioned I'm only plating 0.1 because it's the amount I can actually pour directly on the media. So I've grabbed these ones, I've had them here, and also to be able to make it as successful as possible, considering that it takes some amount of time that we pipette from one tube to another and also on the Petri dish, I want to make my fluid as representative as possible. So for this, normally we used to mix, long time ago, the tubes like this. This is quite a very known technique that we use in microbiology. We just do like this. However, we have gone along far, and I'm quite happy with the vortex that I have over here. It creates a vortex just like the name says. So it's kind of cute when I'm putting it here. It's going to pre-mix very gently and safely my fluid. So then I could have a representative amount, because while I talk and while I show a lot of things, and also while working, the microorganisms tend to sediment, of course, due to gravity. So I've got over here, as well as I mentioned, the vortex, which is ready to set. I really like to work with it on automatic, meaning that I just have to put in my tube inside and it's going to mix it. There are other settings on different vortices. It can also always spin around, and then it continues spinning throughout the experiment, and when you put it in, it still spins and so forth. I like to keep it on touch mode, so then I try to be a little bit more sustainable with the energy that I use. A super must in microbiology when we work in such a setting is your trash can. Well, it's not really just a simple trash can. It has to be a very specific one that later on can be autoclave. It can be sterilized if you want to. So this is made of stainless steel, and it can withstand really high temperatures, and also the surface itself is very easy to disinfect because it does not allow microorganisms to attach on the surface and hide away from all the treatment that we would be putting it in. I always put a bag. We have disposable bags over here because when we finish the experiment, the bag is going to be closed in and it's going to be autoclaved before we discard it into the normal bin, right? We need to keep it safe, and I can't, especially when we work, of course, with dangerous bacteria, we do not want to release them into the environment. So this bag is very important to be able to be placed later on in an autoclave. In different laboratories, there are other protocols. They're all meant to keep us safe, and for this one, this is what we use. I'm going to put it aside. For me, it doesn't have to be, for my rules, it doesn't have to be in the aseptic zone, because when I discard something, I don't care if it's in the aseptic zone, because every time I finish an experiment, I clean up and I leave it neatly anyway. Alright, so we've got the vortex, we've got the bag, we've got the sterile peptone physiological salt tubes. I like to use for myself a rack that is long enough to keep my mind at ease, that I know how to count the 7 tubes. And last but not least, of course, I really need my Petri dishes, right? So I need my Petri dishes where my material is going to end up. 7 tubes, 7 Petri dishes. Sometimes we'd like to add 1 Petri dish from the bag directly. That can also be possible, so then we can just grab 0.1 milliliter from this one and place it on the Petri dish and have our 0 dilution, as we like to say. And I'm saying it's 0 because this has already been pre-mixed with peptone physiological salt, so it's not a real 0, but when it comes to this bag, it is a 0. I'm not going to do it for now because this is just a something to show it to you guys and share with you, so I'm going to put it aside for now and only bring it back when I start my experiment. So I've got 1 Petri dish for every tube, so it means I've got 7 Petri dishes over here, and sometimes the Petri dishes are empty, and it means that you will have to pour your own media in them, while other times the media is going to be already placed inside, just like the ones now for the shorting of the experiment. No matter what you do, make sure your materials are ready before you start the experiment, because there's no room and no time to say, oops, I'm going to need to melt my media and I'm going to have to do something for now. So peptone physiological salt is there. I'm going to put my food sample in there, and when I'm ready, I will eventually put it on the Petri dish. It is very important to be able to track back. So traceability is super important for us in microbiology. We need to be able to track back what was what. And besides the tubes that I've written on them, 1, 2, 3, 4, 5, 6, 7, I also need to adjust my Petri dishes in such a way that I would know in the end what is in here. Why? Because when everything is finished, what I'm going to do is to place them in an oven, and after a specific amount of time at a specific temperature, I'm going to collect them. So I'm not going to know what was in there. So normally we have, as a rule of thumb, we write our initials on the Petri dish, we write what it is, we write the type of the media, the incubation time temperature, and if we have any details like dilution of 7 or 1 or 2 and whatever, that we have to write it over there. For now, I'm not going to discuss about duplos or other things. I'm just going to show you guys how we do this, and we're going to discuss separately in another time exactly how to name your Petri dishes. But what is very important to mention here already is that when you start writing with your marker, of course, it has to be something that it cannot be taken out, right? So you need to be able to read it afterwards. And the important thing is that you will be writing in a curve like this, right? So you're going to be writing in a curve like this on the sides of the Petri dishes, and this is very important because we try to use as less amount of surface on the Petri dish as possible, because this, guys, is where we're going to read our results. So when we're going to collect them back from the oven, from the incubation oven, we're going to read our results on the bottom of the Petri dish. So if you would have it full of writing, that's going to get a bit tough to read. And well, this is also quite standard in microbiology, so we like to keep it standard. So we want to read as good as possible. And for some of you that are wondering, why am I writing on the bottom and not on the lid? It is because the rules are dictating so, because the lids can get out, right? So they can get off, and then you don't know which one was which, especially when sometimes we tend to move things, and more so because we incubate Petri dishes upside down, or like I like to say, bottoms up, right? So we incubate Petri dishes bottoms up, and the reason for that is that we want to make sure that any condensation that happens would be on the lid and never on the bottom of the Petri dish. If it's on the bottom of the Petri dish, all that condensation, meaning water, above your colony forming units is going to be a disaster, because there's going to be a one united front of microorganisms or one united front of a liquid washing microorganisms, and we cannot count that, right? So because we need to incubate Petri dishes upside down, again, as a summary, because of the condensation that should be on the lid and not on the bottom, that is why we write on the bottom of the Petri dishes. And even more so, we want to create a smallest surface as possible when we write, to be able to read our results. So this concludes all the materials that we need to get going. And I forgot to mention one. Before I place everything inside the Petri dish, I'm also going to make sure I've got some tools that are helping me spread very, very well the bacterial suspension or the food sampling or whatever I'm having over there. And these are called Drygalski spatulas, Drygalski spatulas, L-shaped, because they have an L shape, the hockey stick. There are so many ways of saying this. I like the Drygalski spatula because it makes me look smart when I'm saying it. So this is the Drygalski spatula, and because of its favorizable shape, it's going to help me, as you're going to see in a minute or so, it's going to help me spread the bacteria much better on the surface of the Petri dish. So now that I've concluded everything I needed, let's get going. Let's do a dilution series. While we do a quick check that we've got everything I just announced before, I just want to make sure that also my Petri dishes are okay, and I'm going to pretend to start with the last point before I get to it, and that would be basically finishing off writing my Petri dishes. So now I've got a very good excuse to show to you guys what we write on the Petri dish. Again, I've just turned it the other way around to make sure that it's on the bottom, and I'm going to give my initials. I'm Adriana Sterian, so I'm going to write an AS. I'm going to say that this is a PCA Petri dish. I'm going to say that this needs to be incubated 24 to 72 hours at 30 degrees Celsius. But I'm going to do also to say that the date of today, in June 2020, the year is not that important because hopefully we're not going to hold more than a year, these Petri dishes. I'm also going to write that this is my food sample, FS from food sample, and this is dilution -1. Alright, so I've been writing everything on the bottom, very nice and well, as neat as possible. Those of you that actually know me, you know that this is my neat as possible handwriting. Otherwise, you need a PhD to be able to understand my handwriting. So I wrote everything, and with this, I finished off the series of my ready Petri dishes. Before we get to it, I'm going to make sure that I'm working as neat as possible. So this means no jewelries, guys. You're gonna have to keep these very safe. I'm going to put them in my pocket. No jewelries. I've got no jewelries that we can see, so we can keep everything nice and neat. And I'm also going to put myself some protective glasses, which can be your own if they're big enough, or you can have protective glasses from special laboratories. So we are good to go. Going to disinfect my hands, but not in front of the of the Bunsen burner, because that's not safe. So what I'm going to do is to clean with 70% ethanol my hands to make sure I will never contaminate my samples, right? Needless to say, you will be washing your hands before you enter the practical room anyway. All right, are we ready? I cannot hear you. Are we ready? Yes, we are. All right, let's get to it, guys. to do right now is I will start with working with the other way around. Although my dilution series starts with tube number 1 that goes 1 liter in tube number 2 and so forth till tube number 7, I've got a little trick that I'm normally using, and that would be starting plating with tube number 7. Because if I start plating with tube number 7 and I work my way on towards tube number 1, I would hypothetically work my way from the smallest amount of bacteria or none amount of bacteria all the way to the most concentrated sample. This means that this gives me the opportunity to work, if I want to, with the same pipette tip and also with the same dry Galsky spatula. It would mean that I would be saving on my plastics or on my materials, making this experiment much more sustainable. So this is what I'm going to do, and it is indeed true that I might be adding a small amount of bacteria from each and every single tube, counting up towards the plate as well. However, the amount is so significantly less that when we actually count colony forming units per milliliter, it should not really give us an outstanding difference than if we would be working the other way around. can place them now in the incubator and wait exactly as I wrote here, between 24 to 72 hours at 30 degrees Celsius, because this is the time and temperature needed for our PCA for today. And hopefully in a couple of days I could read the results and be able to actually count something. That was it. Short summary. All the materials that you need should be able to be found at the beginning of the video. We make sure that we've got everything before we start what we need, and we finish off with the Bunsen burner that is always left first with a yellow flame, so we are able to see it and make sure that it's safe. And also the next time we will start the Bunsen burner again, we should be able to see the flame. So now we can finally shut off our Bunsen burner very nicely. Also the gas turn has to be completely back, and well, before we get this cleaned up, we are ready to go. Thank you very much for watching, and I'll see you next time.